We are finally able to generalize the use substitution of single variables to sort of planar transformation of two variable functions. The key is that the estimated area of a tiny rectangle inside the xy coordinate system is about equal to the Jacobian times the area of a rectangle inside the UV coordinate system. So you just have to translate the xy coordinate rectangle's size into the UV coordinate. So as long as you have a nice enough planar transformation, you can compute its Jacobian, substitute in the x coordinates and the y coordinates for your proper u and v functions, and then you can take this same integral, except inside you can get the same value as you would have inside the rectangular coordinate system, except with possibly, hopefully, an easier coordinate system to take the integral in. Let's apply the change of variables to this particular integral to compute this integral. No, we probably could compute this integral without it, but we just want to see how it works. Sometimes it's helpful to take a look at the region to see what you want to change your variables to, and sometimes it's helpful to look at the variables inside and see if there's a way that simplifies the integral. The book is giving you an example here that's worth looking at about a strategy to look for a change of variables that makes this sort of diamond region easier to handle. They want to describe this diamond region or the boundary edges in terms of equations and hope they can find a pattern. You can find equations for lines that go through those two particular points. I don't doubt that you could figure out what these equations are by using those points, and it's covered in the book anyways. But visually you can see there are two sets of parallel lines that make the diamond in the middle. This sort of blue line with a slope of 1/3 and a slope of 1/3, but it has a different intercept. And then this other parallel line where the slope is 1 and 1, these two parallel lines over here, but the intercepts are different. Realizing that you have two sets of parallel lines that bound the region, you could say, well, maybe I want to choose a variable equal in some way to this equation where it corresponds to scanning in the direction perpendicular to, say, these two sets of parallel lines. Mathematically, you can get that equation to describe your u by taking the original equation that describes those two parallel lines and moving the variable over to the left. So you move this variable over to the left, this variable over to the left, subtracting both sides. If you do that, you get an x minus y for both of them, and the thing that's changing is just the intercept. But that's a number. And so you can just go ahead and say, I want this combined x minus y to be the variable u, and that tells me I want my u to go from the starting intercept of -1 to +1. That corresponds to, say, this line all the way over to this line. Just shift the intercepts. Similarly, you can do that for the other sets of equations, the slope of 1/3, get your x's, all your variables to one side, and they decide they want to multiply by 3 because they don't like dealing with fractions, and that's fine. The point is that you have a constant on the one side of the equation and the variables the other side. You can set your v equal to that function. That also tells you what your smallest v value should be and your largest v value should be, because that's just the two different intercepts, each one corresponding to the other line. Once you know that, you have two function relationships of your x's and u's and v's. But you want to find out what the relationship should be so that given a u and a v, you can calculate your x. So you just solve for your x and y's using these two equations simultaneously. Again, the book covers that over here. When we look at the next example, I would almost want to use the same strategy. And that means start looking at what the graph of the region looks like. Graph of this mess over here. If I graph the region, I see that it's this trapezoid figure inside here. And I notice immediately there are two parallel lines. So maybe I can use a similar kind of trick as the book, which we'll get to in a second. The problem is if I look at the other ends of the region, these are not parallel lines. So I need some other trick to figure out another function relationship. So let's tackle this problem in 2 steps. First, notice that these 2 boundary curves are parallel. And they're already written in the nice form for me. So maybe I want, just like the book, previous example, I want my u to be an x minus a y. In that case, my u can go between, well, it looks like the smallest this difference is going to be is a 2, and the biggest it's going to be is a 4. In GeoGebra, I made this function that has a slide bar that represents, I called it q, but you want to think of this as being the u, x minus y. And I can slide the button over and you can see, oh, this does scan over the region. It's a line that scans over the region. And it's pretty clearly, it goes from 2 to 4, it goes over the entire region. So the way to think about it is by choosing a u. Again, I'm calling it q here because of the letters in GeoGebra, but you want to think of this as being a u. By choosing a u, I'm getting a list of a line of possible values inside the domain. So I choose a u and I have it, and that u goes from 2 to 4. But what I really need is a very specific point inside the domain by also figuring out how another parameter, v, how I can find a specific point. One way of doing this is that I can think of it doing in steps in terms of I choose a u, I get a line. But I don't want an entire line. I want a point on a line. Now there's a nifty mathematical trick. So the point is I'm not going to be able to do the whole parallel line trick for the v direction because these 2 boundary of the regions, these 2 boundaries of the regions are not parallel to each other. So I'm going to have to use some other trick. But once I see that I can specify a specific line within the region by just choosing my u value, like 2.5 or whatever, I can say, well, I just want to choose a point on the line. And I want to do this systematically so that if I just choose the number v, a value for v, it will give me a specific point on the spread line no matter what it is. Now, there's a trick that I'm sure you have not learned, but is useful in math, where if you choose any 2 points inside your plane, you can choose a point in between them by having a parameter, which I guess I expect this parameter to be my v parameter, but my v is already used for something else, so I'm going to just put s. I'm going to make a new slide variable. Okay. Maybe I don't know what this s is. I'm going to say, well, usually you make this slide parameter between 0 and 1. And I want to choose a point somewhere between k and l. Notice these are the boundary points of my curve. The way the trick works is if I want to choose a point somewhere between k and l, I could think of it along the line as being a certain distance on a scale of 1 to 0 away from k and away from l. Or I could think of it as sort of being like an averaging operation. And if we just also think of this operation as maybe this is actually the terminal point of a vector, this k and this l is the terminal point of vector. You do this because you have an idea of scalar multiplication and addition. Then you can say, well, in terms of scalar multiplication and addition, I want to multiply the scalar s times my vector k plus the exact opposite of scalar x, so 1 minus it, times my vector l. This would give me some point along the line. If I change that scalar between 0 and 1, it's guaranteed to always give me some point on the line. So now, between shifting my, what I really wanted to be my v, but I called it s, a slide variable, and my, what I really wanted to be u, but I called it my q, this slide variable, I can choose any particular point inside the region in terms of just those 2 parameters. But how do we write that as mathematical equations? Well, it's almost all there. The key to our nifty trick is the fact that we always have the k is always the y-intercept of the red line, and l is always the x-intercept of the red line. And if you know enough about equations, you could figure that out. The y-intercept for whatever u is for this particular line is going to be 0, negative, whatever u is. The x-intercept is always going to be u, comma, 0. That's the coordinates of it. Our rule was we multiply this as a vector, if you want to think about it, by a scalar of, say, v. So instead of s, I'm using v. For the first point, find 1 minus v for the next point, and then add the two. What you get is the component vector form of the equations that describes any particular point in the x-coordinate and the y-coordinate over where your u can be between 2 to 4, which we got by the two parallel lines, and your v could be between 0 and 1, which we got by that rescaling of these sums of vector endpoints of those lines, those intercepts. All that work gives us the transformation, a planar transformation of this box region or rectangular region into the actual trapezoid that we started out with. The explicit equation is written over here. If we'd like to use the change of variables for the integral, we have to figure out what the Jacobian is first. So we compute the partial derivatives of our coordinates, which we have listed here. We fill them into the appropriate 2x2 matrix, take the determinant. Things cancel out and we're left with a negative u, but the Jacobian, when you actually take the integral, we take the opposite value of it. So we get rid of that negative sign on that u. The next step for the integral is substituting in replacing your x and y values with your functions here. Now, we happen to choose that if it's x minus y, we knew it's going to be u, and that's what I see here, so I can just shortcut that and write that response right over here. So now I've done the substitution where I replace my xy variables with the appropriate mess over here that simplifies down to just a u. It becomes a u squared on the denominator. I use my Jacobian right over here, replace my differential for area with the appropriate Jacobian times the du dv. And the last part is my limits of integration. Go from being these linear functions to regular rectangular coordinates. Now this integral, admittedly the above integral probably wasn't so difficult if you computed it directly, but this integral is totally doable. And there you have your answer.